All right, howdy chemists. So you've now completed the modeling lab and had some time to do a little bit of reading and exploring what we call our molecular geometries. So the actual shape that molecules take in space as opposed to maybe what they look like on paper. What we're going to learn about here, our molecular geometries, are based on what we call is based on what's called the Vesper Theory. So Vesper. And Vesper stands for Valence Shell Electron Pair Repulsion Theory. Now, that's not necessarily something you need to know, but it's kind of interesting. And its name is, in fact, telling you a little bit about what it's based on. It's essentially based on the idea that, okay, let's break this down. Pairs of electrons, and we know that around a central atom there's going to be pairs of electrons. There's going to be some that are shared pairs of electrons, and there's going to be some that are unshared and are still around that central atom, often called lone pairs. And those electrons, those negatively charged particles, repel each other, and therefore they push away and try to get as far apart from each other as possible, and that resulting movement around the central atom results in the overall geometry of the molecule, which can then be confirmed with like crystallography. So the gist of the model, or the definition of the Vesper theory, is a model that we use in chemistry to predict the geometry of individual molecules from the number of electron pairs surrounding the central atom. So we're going to have some central atom, so something like here's our carbon, and then we have things bonded to it, and some of those then are going to reflect shared pairs of electrons, and some are going to be lone pairs that are then left around that. And that movement of those electrons as they push around each other are going to give us our overall shapes. And there are 5 main shapes that we learn in this class. There are actually other molecular geometries, but this is a good starting level for our introductory chemistry. And we're going to explore them right now, some of which you built during that lab. We're going to explore them by looking at the Lewis structures of each of these and translating that into then what shape would that be in an actual 3-dimensional world. So we'll start here with CH4, which is actually methane. So CH4, or methane, has a Lewis structure that looks like this. We have the central atom carbon singly bonded to four hydrogen atoms. Now you would predict that our analysis of this substance based on this picture that we would find there's a 90-degree angle right here. That's what it looks like based on the picture, right? But in actuality, when we make those measurements, we find it's not 90 degrees. It's a little bit bigger. It's 109.5 degrees, meaning they're actually a little bit further apart. So let's then apply the Vesper theory to figure out why. So each one of these lines, each one of these Lewis structures is actually representing a pair of shared electrons. So these are actually, each one is 2 electrons. And they are all pushing away from each other. The valence shell electron pair repulsion theory. So these valence electrons are trying to be as far apart from each other as possible. So think about like little kids trying to, vying for a position on the couch to watch a movie on family night. They're all pushing on each other and trying to get as much space as possible. And the electrons are doing that. So these ones are pushing on these ones, which are pushing on these ones. Now, on a paper where we're looking 2D, it looks like the farthest apart they'd be able to be would be that 90. But we have to remember that molecules exist in the 3-dimensional world. So if you actually took like 4 balloons and you tied them together right here, they would eventually, they'd kind of jostle each other into a more 3-dimensional shape, trying to be as far apart as each other as possible. And you saw this in the lab through this structure here. You didn't build this exact one, but this overall structure right here. And this angle right here, this is wider than a 90-degree angle. And that's because these electrons are pushing each other, not just in the 2-dimensional world that it looks like on the page, but the 3-dimensional. This one pushes up, and this one can push this one back into space. And that's one of the reasons that sometimes chemists will instead use dashes and wedges in their Lewis structures. The dash is the atom that's going in behind. The solid lines are the ones that are directly in line here with me or my page. And then I use a wedge, sometimes solid filled, sometimes not, it doesn't matter, to show that it's coming out at me. So what is the shape that this is when you have a central atom and 4 things off of it with no lone pairs? Well, we call that a tetrahedral. This is our first shape. Tetrahedral. So tetrahedral. And you can really tell a tetrahedral when you build it, but for a Lewis structure, what I would expect is I have some central atom and 4 things bonded off of it, and then no lone pairs, because lone pairs get to push as well. And if there were lone pairs in addition, I'd expect that angle to be a little bit different. A memory tip here, this word tetra, think Tetris and the little boxes, and you can envision 4 little boxes, actually means 4. And so there's 4 things off the central atom, and that will result in a tetrahedral molecular shape, whether it's carbon and hydrogen or other things. If this is my Lewis structure, I should be able to apply the Vesper theory to predict that these molecules are going to push themselves into this overall shape. Do I expect you to memorize all these bond angles? Not really necessarily, but I do expect you to have an idea of maybe an approximate value. Is it 90 or is it greater than 90, or would I expect it to be less than 90? So there's our first shape, which we're going to see when our central atom has 4 things bonded off of it and no lone pairs. So moving on then to NH3. That was the next one we were going to look at to introduce our 5 structures. So NH3, this is an ammonia molecule. And if I draw, you either have or will learn in class how to know what the Lewis structure is, but for now I'm going to give it to you. When I draw that Lewis structure, I'm going to see that I have 3 hydrogens single bonded off of my nitrogen, and then a lone pair off the nitrogen. So consider our octet rule. Our hydrogens have full valence shells because they each have 2, so they're isoelectronic with neon. Helium. I was thinking about nitrogen. And nitrogen, 2, 4, 6, 8. Nitrogen originally had 5 valence electrons, these 2, and then 1 of each of these, and through sharing, it fills its octet rule. So you would expect by looking at this, going back to our tetrahedral, that we would expect to see this have a bond angle of about 109.5, right? They're all going to push each other. These, they're all pushing each other, and our lone pair here at the top, vying for a position on the couch. But that's not actually quite what we see. The bond angle is closer to 107. It's a little bit tighter. 107 degrees, meaning these shared electrons here that are pushing around the central atom and trying to be as far apart from each other as possible, they're a little closer than we expect, a little closer than we see in our tetrahedral shape. Why is that? Well, the reason is these lone pairs. So this lone pair here at the top, they also participate in the pushing on each other. They repel, but they actually repel a little bit stronger. They're like the pushier kid on the couch with the bigger elbows. And so they end up getting a little bit more space and kind of pushing down a little harder on that overall, those other bond angles, forcing them to be a little bit closer together than they would otherwise like. Now, the reason for that, you don't really need to know, but it has to do with the fact that they're not being canceled out to any degree. They're not interacting with a nucleus on the other side. Whereas these electrons, that negative force is getting dissipated a little bit with a nucleus on either side, and since they don't have this, their negative charge is, you could think of it as more concentrated. And so because of that, we do see this slightly tinier bond angle, forcing them a little bit closer together. Again, not the 90 degrees that it might look like on the page, but also not the 109.5 that I would expect. It's a little bit smaller. So what do we call this shape? First of all, let's look at it in the model. This is how you would build that. We see this open hole here represents the lone pair. And the reason the model kits have that is because actually nitrogen sometimes will take on another hydrogen, but it's no longer a neutral molecule when it does that. And we might talk about that later. That's an ammonium polyatomic ion. So this shape that our ammonia molecule takes is called trigonal. If you call it trigonal, that's fine too. Trigonal pyramid or trigonal pyramidal. Pyramid or pyramidal, and either one is fine. I'll put in little parentheses. Pyramidal, trigonal pyramid. So the trig or tri comes from the fact that there's three things off the central atom. So we have some generic central atom, and then I should have three things bonded. And they could be single bonds or double bonds. It doesn't really matter. I'm showing single bonds in the structure. And then the pyramid comes from the presence of the lone pair. Now, why? Well, look at this from the side. Notice this raises up a little bit. There, when I do it that way, there you can see. It raises up a little bit like a pyramid. So it's a little bit more pyramid shaped. And that comes from the fact that, think of it like my hand. And I've got the lone pair on this side. I've got all these electrons trying to be as far apart as possible. And the lone pair pushes down harder, and so that raises it up in space a little bit. So you'll recognize a trigonal pyramid in a Lewis structure by three things off the central atom and one lone pair. Trig, tri, three, and the pyramid comes from the presence of the lone pair, raising it up into space a little bit. Now let's look at a kind of similar structure with a twist. Oh, sorry about that. Don't worry, she's still alive. And this is one that you built in class. So its chemical formula, or its molecular formula, CH2O. You built this during lab. This is actually the chemical formula for formaldehyde. So its Lewis structure, carbon, double bonded to oxygen, got some lone pairs off of that oxygen, single bonded to a hydrogen on either side. So let's consider if their octet is filled. The hydrogens are, because they only want two. The carbon, 2, 4, 6, 8, that's got a full valence shell. And the oxygen, 2, 4 from the lone pairs, 6, 8 from the shared. So it does have a full valence shell. So when I go to build this, you're going to notice, here's my little model, it has three things off the central atom as well. And these pairs, these shared electrons, they're pushing on each other as well. But there's no lone pair here to push this either up into space or down and away from it, making a very flat or planar molecule. And the bond angle that we see here is actually quite a bit larger than the other ones. This is 120 degrees. They get to a lot of space on the couch because they're not going up into space or down. They can be in this flat plane. So farther apart from each other due to that lack of lone pair. And we call this trigonal, so there's that word again, but planar this time because it doesn't rise up into space. Now when I turn this molecule this way, you can see a little bit better how they're all lying in the same plane. They're all lying the hydrogen, the carbon, and the oxygen. They're all in the same plane, as opposed to here, our hydrogens that are a lower, depending on how you hold it, of course, they're beneath the nitrogen. The nitrogen is more elevated, so it's sitting in a different plane than here. So we have three things off the central atom again, whether double, single, or triple bonded, but then we have no lone pair. Probably a better way to draw this really would be this. Show they can get really far apart. No lone pair to raise it up into space, so it lies in a plane. Now I'll tell you, trigonal pyramid and trigonal planar are the two that students confuse the most often, and it's because their names are so incredibly similar. So it's that lone pair difference The trigonal pyramid has a lone pair, which is what causes its atoms to push down and then be raised into space as those electrons are pushing on each other and trying to get as far apart as possible. And the trigonal planar doesn't have that, and so they're allowed to stay in the same plane, really spread out in space. So you wouldn't really use dashes and wedges here because you don't need to, because they all lie in the same plane, so I would use solid lines for any of them and it still communicates the three-dimensional nature. So next we're going to look at water. We're familiar with water's chemical formula, and a lot of us are also familiar with its structural formula. So what would you predict the bond angles to be here? This bond angle between these. So these hydrogens, the bond here is they're trying to get as far apart as possible. The repulsion of these electrons pushing around the central atom. What would you predict? We have 109.5, we have 107. Well, it's a little bit tighter right here. It's 105 degrees. A little bit more, getting pushed in a little bit further. So why are these electrons, these two electrons and these two electrons, which are repelling each other, willing to be that close when they want to be as far apart from each other as possible? Why don't they do this? Be really far apart. Well, it's the presence of this two lone pairs up here. So remember, they're apart. You don't have to be shared to be participating in the pushiness around the central atom. And those lone pairs actually push harder because that force isn't being dissipated. And so they're like, their negativity is stronger. And so they're going to push down a little harder and force this bond a little bit closer together. So I expect that bond to be closer in a molecule like this. What do we call this? This is my personal favorite name, bent. It's also called angular, but bent more often, so we'll go ahead and go with that one. You can call it angular and I'll know what you mean though. It's a bent molecule. And we essentially can see a bent molecule from two different ways. We have two bonds off the central atom and two lone pairs, like we see with water. Or if you have one bond off, or two bonds off the central atom, again, that's kind of the critical piece, and one lone pair. Now this one would have a wider angle, be able to be a lot farther apart. In fact, it would have the same bond angles as our trigonal planar. But we can't call it trigonal because it only has two things. So the two things off the central atom is kind of the critical element here. We need to have two things off the central atom and at least one lone pair to account for the bent shape that we see with these molecules. And our last shape we're going to learn about, you built in lab as well, with our carbon dioxide molecule. So you might remember the structure that you came up with in lab. For the Lewis structure, it's a carbon double bonded to an oxygen on either side. And both those oxygens have lone pairs. You'll notice that there are often lone pairs on these terminal or outside atoms, but the overall geometry is really about the electrons around the central atom. And so we're paying attention to them because this is what determines, this is the couch that the electrons are all fighting on. So you'll notice even in the way I've drawn it, I've given you a little bit of a hint in terms of its shape. How this little group of electrons, these pairs of electrons and these pairs of electrons. Now these guys have to stay together. They can't go moving all around the atom, and that just has to do with the way the orbitals overlap. So this little group wants to be as far apart from that little group, and what's the farthest they can be? On the complete other side. So our bond angle here is the angle of a line, 180 degrees. So when we built this model in the lab, we see it's a straight line. And so we name this, again, I like the creativity. I like it when they make sense. It's easier for my brain. A linear molecule. And you can have a linear molecule in many different ways through many different bonds, but the gist of it is going to be some central atom and two bonds off of it. Now this could be a triple and a single, this could be a double and a double, but it's bonded to two things. bonded to two other atoms from our central atom, whatever they are, and then there's no lone pairs off the central atom, because otherwise they would push these into some smaller angle than 180 degrees. So there you have it. We have our 5 shapes that we're going to learn about for this class. We have our tetrahedral, our trigonal pyramid or trigonal pyramidal. We have then a trigonal planar, so similar looking, but it's the planeness, the 3-dimensional part that makes them a little bit different. And then they do have slightly different bond angles. This has a wider bond angle. Bent, like a water molecule, or linear, like carbon dioxide. And this matters because the molecular geometry plays a big part in the polarity, and the polarity plays a big part in the physical properties of a substance, especially things like melting and boiling point and solubility in water, which are really kind of critical properties for different chemicals. So it's very important that we learn to take a Lewis structure or draw a Lewis structure and then be able to correctly infer the molecular geometry that it would be, which one of these is it, applying what we know about from the Vesper theory. These electrons around the central atom, these paired or unpaired lone pairs, want to be as far apart around this atom, as far apart from each other as possible.